You can visualize it in the camera. So this is, we are dealing with the individual molecules. So when I said you use some techniques, like for example in drug design, you need to have some receptor structure, some protein molecule structure. So you cannot draw the structure, so you download such PDB molecules directly from some website. And when you want to deal with the material design aspects and you want to deal with the structures like graphene or carbon nanotubes, fullerenes, so then you need to have some third party software like this Avogadro I have given. This is one of the example where you can construct such things. So these also you cannot draw directly by the your hand. So you have to download the structures based on the requirement, and then you have to do the required processing. So this is what we have understood. So still any question anybody has? Okay. So I will move to the next section. So last time I said we are initially going to deal with only the structure part, the chemical structure representation. But now, using these structures, we need to find out some desired chemical and physical properties or biological properties, and that we have to use it for the screening purposes. So you can consider here, this is initially you have built some structure. Now you know how to build the structure using some softwares, how to do it for all the different molecules. We are today going to learn the smiles representation. So you'll get again confidence with all the different structure which are not which you can actually even draw by hand, how you can represent them by simple line notations. That will try to learn. So just to have idea about what exactly how the flow is going for our course, like we are initially having just some structures. Based on that, we want to ultimately do some screening. So we are interested in some kind of property prediction. So two techniques majorly we are going to focus on. One is called as QSAR method that I mentioned earlier, quantitative structure activity relationship, and second method is docking, which is the molecular docking method. So in both the methods are different in such a way that initially you can consider just the structure I said. So structures are simply, they do not, they are like some dead bodies. They do not have any soul within them. So they do not understand how to interact with the other compounds. So initially based on the structure also you can estimate some properties, like you do not know how one structure, if you have created a benzene structure, how it is going to interact with a water molecule, but still based on the structural features of the benzene you can predict certain properties, and using the some basic properties you can estimate some even bigger properties which can be utilized for screening purposes. Then it can be made more sophisticated. These dead bodies can be can undergo some molecular modeling process. Means these dead bodies can have some soul within it, like all the structural features along with the structural properties. They can have some kind of charges, some kind of parameters. So they will be understanding how to interact with, how to electrostatically interact with other compound, how to interact have the van der Waals interaction with the other compounds. So that what we do, this is like more sophisticated method than the previous one. We all these molecules undergo some molecular modeling, and then by having some interaction, like for example, some interaction between a protein and ligand molecule, you can have some kind of property prediction, and that you can use for the screening. So slowly you will understand what we are having this as a flow, but just having given the example that what a structure we are building, ultimately we are going to do the property prediction. Okay, just a minute. Okay, so last time I mentioned to you uh, this smiles representation. This is also one of the chemical file formatting, and like I said, the extension for this is some dot SMI file format you can have, and you can represent any compound in terms of simple line which is having some grammatical rules. So what are these rules? There are so many file formats, but this is specially we will use because at least in this particular case where you have to deal with a lot many compounds together in a single file. So putting all those compounds in a single file is comparatively useful when you can represent them in a simple line notation. So this I have given you last time some idea that it is a linear rotation and it is having some grammatical rules. You can consider this is having some alphanumeric characters. So capital O, you can see C, then sometimes they become small c, there are some numbers, some brackets. So all these things you can consider, you can represent any molecules in simple line. It can go into the multiple lines, depends on your space, how much you are having in your file, but that you can consider this is a continuous representation. Okay. So we have seen this. This is a more compact representation compared to the connection tables that we have seen, like normally in the PDB file format you have seen. There also you see some connection tables. So you can consider they are particularly useful for storing and transmitting large number of molecular information. Okay. So if you see in general, like all these things I have taken from this particular resource in very much detail. They have given all the information related to smiles representation. So if you want to categorize this, normally you can consider there are 5 generic rules. Okay. So if you see these 5 generic rules, they are related to your atoms, then bonds, some kind of branches that will come into picture, then some kind of rings, like in benzene ring, you have seen some kind of numbers are coming, and certain times the two molecules can be disconnected. So how to represent all this structure? So we'll just start with the simplest one, how to have this representation of atoms. So earlier you have seen the representation for propane. So it was capital C, capital C, capital C. So you can consider the simplest thing that you can have the representation. It is the single capital C, and you can consider this is not just a single carbon atom, but all the 4 hydrogens that are attached to it, it is implied. So when you want to represent methane, so you have to consider that the carbon atom is having all the 4 hydrogen atoms attached to it. So in the same way, you have ethane and propane. So you can represent all the structures in which the hydrogen atoms can be completely omitted or you can include. So based on that, it is called as hydrogen suppressed graph or hydrogen complete graphs. Most of the time, whatever things we are going to use, they will be having hydrogen suppression so that least processing should be there. So anytime, suppose if you want to represent a particular atom and you don't want to specify its the hydrogens attached or something, so any non-hydrogen atom, how you can specify, you have to mention it into the square brackets. So this is like the when sulfur you are representing, suppose if you just write down S, so it will having the meaning that the hydrogen, it will be the valences will be satisfied of sulfur with the hydrogens. But if you are putting the square bracket, means that it is only the elemental sulfur you are considering. Same thing with the code. Second letter normally you write in the lower case. So suppose if you see all these are valid representation. If you write simple carbon, phosphorus, nitrogen, but I said all these things if you are not putting any brackets, meaning that its valences are satisfied. So in certain cases, you have multiple valencies for the particular atom. So when you are not writing any brackets, so it is representing the lowest normal valency. For example, like for boron or carbon, it is okay for, but for nitrogen, the valency can be 3 and 5. The phosphorus 3, 5, sulfur 2, 4, 6. So the lowest, like here in this case of nitrogen, 3 will be represented for phosphorus 3 and sulfur it will be 2 that will be considered. So if you want to represent any of this molecule, And if you want to also represent some ionic structure, so in the square bracket, you can actually explicitly mention the charges also. For example, a proton, you can mention H plus for the hydroxyl ion, you can mention OH minus ion, so this can be mentioned specifically. If you want to write down a molecular hydrogen, so this can be mentioned also as in square bracket hydrogen, and next again you will continue in square bracket hydrogen. So instead of mentioning H2, you can also represent in this particular way. So like if you want to practice this, like just for the atomic thing, and for nitrogen, if you want to see what exactly comes, so you can practice all these things with Open Babel. Just see. Like suppose here in the smiles representation, if simply I'm writing the n and I'm already clicking into generate 3D coordinates and output I'm giving the XYZ file format. So you can see when I'm writing the capital N, it is giving me NH3 ammonia it is producing. So the valency that it is taking the lowest normal valency of 3. But if you want to specifically mention, like suppose if I'm taking sulfur, the lowest valency of sulfur it will take 2. But if I want to mention any higher valency, so as H, suppose if I want to mention the valency of 6, so I have to specifically mention in the square bracket. So all 6 hydrogen will come into picture. So in this particular way, whatever doubt comes in your mind, you can for any smile string, you can simply open the Open Babel software and you can try practicing whatever strings you want to. You have any doubt with. Okay. Now about the again as we are dealing with the atoms, like here one thing to know that whenever you are mentioning the capital C means you are dealing with the some aliphatic structures, whereas when you are dealing with the small c means you are dealing with some kind of aromatic structure. So this in detail we will try to understand this kind of structure how to represent. For now, just know that the aliphatic is represented by capital C and aromatic is represented by small c. Now for bonds, which is the second thing you should know, like most of the time when two things, nothing is in between them, you can consider that they are bonded by the single bond. But you can also specifically mention a dash between them to mention how the two things are attached by a single bond. Then you can consider like the double bond, it is represented by the equal sign. Then if you have a triple bond, it is represented by the hash symbol. And the aromatic bond, so many times you write the small letter, but if you want to keep the capital letter itself, so the two C in between them, you can have the colon symbol. So that will be representing even though you have represented in the capital representation, but if you are putting a colon between them, means you are dealing with the aromatic structure. So here it is said that if any simple structure, if you want to represent it in the smiles file format, so what you can do, you can simply delete all the hydrogens attached to it, and what you ultimately get is the smile representation. Like if you focus on this particular structure, if you remove all the hydrogens from here, and what remains is C double bond C C C. So either you can mention the single bond between them or you can skip it. So all are the valid smile string and whatever is remaining is the smile string. Now this is like directly you can get from this, but one more representation you can have the opposite thing also if you take, like if you start from the item O and then if you end with the symbol and with the the carbon, still it is a valid representation. So you can have it in the from the both sides. You will get the same structure. Then the next thing is about the branches. So see any structure where you have some groups like any isogroup groups or something. So this representation, only one rule you have to remember that implicit connection to a parenthesized expression is to the left. Means again, suppose if you want to represent the structure in the smiles form, what you have to do, again remove all the hydrogens from this, and what you get is CC and then CC. Now here one new thing is there, that in bracket you have capital C, capital C. Okay, so what is the meaning of this thing, that whatever connection you are having, so to this nitrogen, what connection you have? You have CC. Okay, so this connection should be represented, implicit connection to a parenthesized expression is to the left. So this is the branch that has arisen, C and C. So they are saying the connection, it should be mentioned to the left, from where it is actually arising, the nitrogen, that should be present on the left hand side of this particular branch. I hope you have understood this. Okay. This is applicable even if you are reading the same structure from the opposite side. I said earlier, you can start reading the structure from the opposite side also. So if you start reading it from opposite side, so what will happen? Capital C, then this nitrogen should come, and then CC. So I'm just continuing this in the opposite direction. So CC and CC, and the branch should be mentioned in this bracket CC. But in this case also, this nitrogen, the nitrogen should not be on right side. It should be always, in whatever way you are representing, the nitrogen should be always on the left side. Okay. If there is any doubt, please ask. So same structure you can see again, remove all the hydrogens from here. So here only one CC, then this attachment should be there of C and oxygen. So you can see in the bracket C is mentioned, and to this particular carbon which is on the left side, to this the double bonded oxygen has been specifically mentioned, and then the final O. If you want to try this on the paper, you can just give a try what exact structure comes there. I would say just suggest like for 30 seconds or 1 minute, just try these structures on the paper, like how exactly the final structure you should get when you try to visualize in the open bar. Okay. So here if you want to focus, what you'll do, whatever is in the bracket that you can ignore initially, just draw this whatever is outside the bracket. So this should be linearly connected. This carbon should be connected to this carbon linearly, and this carbon should be connected to this. Then to this carbon you go and attach C, because in the bracket this is mentioned, and then to this carbon you can mention a C which is attached to another C, but this particular carbon has a branch of C, so it will come like this. I hope you are getting what I'm trying to say here. Okay, if you see the actual structure, it will look something like this. Observe the branches. Fine. Okay. Now a little bit more complicated. Now, if you consider the cyclic structure, like benzene is the example for you. So suppose here, which is this particular structure, I have represented this in this particular form. Can anybody tell the name of this structure? Cyclohexane. Okay. So here all the aliphatic carbons, we have to represent it in capital C. So you can consider the cyclic structure. If you want to represent the rule you have to follow, you have to break one bond in each ring. So here in this particular case, you have only one particular ring. So you are going to break one bond anywhere in this particular ring. Okay. So they have shown, like, just remove the hydrogen from this. So this is the structure becomes for capital C, and they have broken here. So here the bond has been broken. So now the number they have given, some number they have assigned, they are saying the bonds are numbered in any order designating ring opening or ring closure. So whatever you are considering, so at this particular, so this bond you have uh, broken, so C1 and C1 that has came here. So you have so then what you have to do, this leaves a connected non-cyclic graph which is written as a non-cyclic structure. So what you have to do, just simply start reading the structure from the one open end to another open end. So it will become C1 CC C C1, or from the opposite side also it will come to the same level. Fine, any doubt here? Okay. Now here the number 1 has been given. Suppose a doubt comes to your mind. If I write here, instead of 1 1, if I write here 2 2, whether it is still the cyclohexane or not. So that what a, doubts like this comes to your mind, just try yourself and see what structure it's come. So I can give the hint, you can write here any number, but this particular number should match with the here. If you are writing here 2 and here 1, it's not allowed. So if you are writing here 2 and here also 2, so still it will be considered as cyclohexane. Fine. So for benzene, if you want to represent, what will you write? What will be the smile string for benzene?
So instead of capital C, we will write small c.
Small c, same structure. Okay. Now let's consider in the cyclic structure, we are just making it more and more complex. So in the cyclic structure, suppose if you are having some branches. So for example, here this particular structure is given and this is where the ring is. So this particular ring, when you have to break the bond, I would suggest never break anything like a double bond or something. Wherever you find a single bond, only break there. Okay, because double bond should come into your structure. Single bond, it is assumed that whenever you see show any connection, so that is representing a single bond. So here you have so many options. So in this particular case, what they have done, there they have made the breakage, and this they have given the name C1 and C1 that you can see here. Now again, this you are converted into a linear structure, so you can start reading this. So, but here also there is one branch for bromine. So how this can be represented in the two form? Start reading from one end to another open end. That's what I said earlier. So what you can do? CC1, CC1, double bond C, C. Then in the bracket they have considered bromine, and then they have continued with CCC1. Fine. Or what you can consider, this entire thing you can consider after C as the another branch. So C1, CC, same thing what you had earlier. And the other thing is considered as the branch. So capital C, C1. And this is continued. This capital C has shown there is no bracket or something. This has continued with the bromine. So this C is attached to the bromine and branch is this. So in this particular way, you can represent, so you do not have any like preferred input, you can always use anything which is comfortable to you. Fine. Okay, now see this structure, this is called as cubed. Okay, if you see it in three-dimensional form, so it will form a cube of all the carbon atoms. So now this is also a cyclic structure, but this is having now more than one rings. Okay, a single atom may have more than one ring closure. So this is the example they have given. And now again our rules should be same as previous one. So what rules we have learned and what you are going to follow here? Can anyone just tell me how what should we do when you want to approach to this thing? Which rules you have learned for the rings related stuff?
We need to break the cyclic form and make it to single line.
Yeah. So first thing is you have to break the rings. So but now here, how many rings are there? You have so many rings actually. If you can consider this is the particular ring you are having, that can be that is not always the hexameric structure you can have. You can have pentameric structure or this like quadratic structures also. So you always have these rings, but here there are multiple rings. So but one rule was there that in one particular ring you will only break only one particular bond. Okay, so that rule you have to follow. So suppose if I am considering this thing, so I will break one bond. But also another rule was the entire structure you have to convert into the linear structure. Okay, so this thing we have ultimately converted into a linear structure, like from C1 to you can read like this. And this is what if you simply join this milestone comes into existence. So what exactly we have done here? So first, suppose you can start from anywhere, but I will just follow this example. So I have broken first this particular bond. So here, this was bond number 1. Okay. So what numbering I will give here? I can give any numbers, but here I am putting as first bond I have broken. So C1, C1. Okay. So this particular ring has been taken care of. Then if you are moving to this second ring, so here they have broken here the this particular bond, second bond. So you can see here how the numbering is been given. It one was already one already existed. So to one more number was added further. So this is not 12. This is you can consider this is 1 2 C1 2, and here you have given the number 2. Okay. So here it was C1, it became C12 and it became C2. Then later on you have another bond breaking here 3. So this became C3, C3. The same way one bond in each cycle you can break. So here again one bond is broken C4, C4 has been made. And then here another bond, so C5. So again this 5 number was broken. So here it became 2, 5 and this became C5. Okay, so that you have to follow properly. So whatever then remains, that everything you have to attach properly. So C12, you started from this side. So C12, C3, C4, like this you have joined. So this you can do in any particular way, but these two rules you have to follow. You have to convert into linear structure and you have to break one particular bond in one cycle. Let's take this example. Now here, which bond you will break? How many bonds you are going to break here?
Only one, sir. Two, sir.
2. So there are two cyclic structures, so you have to break two things. But only thing you have to remember, never disconnect the structure yourself. Like you don't convert it into two different molecules. Otherwise, this is considered to be a disconnected structure. You have to break the bond somewhere in the ring itself. So you can break here, 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 anywhere, or on this side, the second ring, like this. So in this particular way, you can break it, but don't break at the center. And then again, you just start like if it is given, you are given to this oxygen number 1, O1. It is being eventually attached to this C1, so it has ended here. Then this nitrogen this carbon is attached to this nitrogen, which you have given number 2, and this nitrogen will go from C, 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 and ultimately it will come to this bond, second bond you have written, so C2. So observe the connections and how they have joined with each other. So C1 is connected to N2. Okay, so these are there for practicing. I would suggest you to practice and try to visualize also. So you can have for the same thing. Suppose if I ask you in the exam, like for a particular smile string, for a particular structure, give me the smile string. So always you will, different students will be having different smiles representations. But if I ask you to give me structure from any smile string, so that structure should be always the same. Okay. Then there are some small rules and some specific rules which are again more complicated. But this some small rule, like if you have any disconnected structure, like I said earlier, you can convert this into a disconnected structure. So this will become actually instead of one, two things. Suppose in reality you have two different things. Like if you want to represent a sodium ion separately and this particular ion separately. So these I said ions you can specifically mention in the square bracket, but the disconnection should be mentioned by a dot symbol. So that dot should come in between and then the remaining thing. So this is actually saying that there are not one particular atom or molecule, but there are two. Okay, so more disconnection, more molecules are there in your representation. So many times these kind of things they use for representing chemical reaction when they want to mention multiple reactants or multiple products. Now, one of the last complicated thing to mention, like you can have so many isomers. So first you can have isotopic isomers, so like carbon 12 or carbon 13. So this number of carbon 12, if you want to represent, like you want to represent their atomic mass, so you can have this as 12C in the square bracket. So specifically you are mentioning this is the 12, the carbon with atomic mass of 12. Similarly, the other things you can specifically mention. Now here, the more complicated isomeric form, like if you have the cis isomers or trans isomers, so you can see the representation, like for example, this difluoroethene, if you see the representation, see here the fluorine atom, like hydrogen, again when you are representing the smiles form, you can skip while representing, but you have to focus on the other heavy atoms that are attached to each other. So when fluorine is attached to this carbon, then double bond, and then this is how the representation can be. Or if you remove the hydrogen from here, so fluorine can be attached to this carbon, and then you have isomers like this. So this particular thing, anybody knows any term for this? Like when we have a carbon attached to fluorine, so this is a bond for you. When the fluorine is attached to carbon and then another carbon, this is the angle that is being formed. Similarly, there is one more type of angle which you can represent for four atoms like FCCF. What is that particular angle? It doesn't even know the terminology for that. Like bond is between two atoms, angle is between three atoms. Similarly, yes. So dihedral angle is the between the four. So instead of having the angle directly between the three things, you find out the angle between planes. For this, I think you have to consider the three-dimensional representation that I cannot show you here, but you can consider this is like one plane that will be formed by these three atoms, and the another three atoms will be forming the another plane. So what is the angle between them? That is, you can consider it is E or Z, that is trans or cis representation. So here, what is the dihedral angle? If it is trans conformation or trans, it is 180 degree. Okay, and when it is like this, if you are representing, so the dihedral angle between the plane formed by these three atoms and then these three atoms, it is the 0 degree. So this you have to have little bit 3D visualization. So you can consider this is the C representation. So you can see when you want to represent the transform, so you can have the F and then a particular like the forward slash has been mentioned here, like that will represent this particular thing. So C, double bond C, and again the forward slash. Okay, F. But the same thing if you want to use for the same thing if you want to use the backward slash also you can use, but for a transform it should also have the same way of representing the another bond. If one thing it is like having the connection like this in the transform, if you are representing like this is correct. But one of the form you are considering in the opposite way, so other thing also should be represented in the same way to represent in the transform. Okay, and same thing for C's. There should be both the bonds should be opposite. So F forward slash and then C backward slash. Like this was forward, this was backward, like this. If you are want to represent in the opposite way, so if one is you are considering to be backward slash, another should be represented in the forward. So this more and more complicated structure, you can have the representation like this. Okay. Now here the most complicated thing, it is this tetrahedral chirality. In tetrahedral chirality, what you have, like suppose this is the example it has been given, like at the center, this is like you can consider structures like amino acids. So in amino acids, you had one carbon atom at the center, then the carboxylic acid group was attached, amino group was attached, and one hydrogen was attached, and one some functional group R. So in this same way, some structures will be there which will be always having some kind of tetrahedral chirality. Now tetrahedral chirality is one of the representation of chirality. There can be more kind of chirality, but this is one special case. So in this particular cases also you can have Smiles representation and you can come to know whether it is the structure is the right-handed or left-handed. Means you can consider like if you see this structure and this structure, they are not the same. You might have studied this that these are called as some chiral structure or asymmetric structure, even though they look the same, but you cannot superimpose them on its mirror image. Means if you put one hand on the another hand, not in the opposite way, but facing the same palm, like the palm side on the same direction. So both the structures won't be able to superimpose on each other. So these are the chiral structures. So when you want to mention the symmetry, then you have to use some extra symbols. So this particular symbol they use it is the add symbol or 2 times add. So what is the meaning of this symbol? You have to consider this particular structure. Like the earlier structure I have represented in this particular form, but for chirality, it is very difficult to understand how they are actually arranged. Okay, so this chirality actually you can mention by this. Like here they have mentioned unspecified chirality. Okay, here they have mentioned specified. So in unspecified you don't have this symbol. In specified you have this symbol add or at. Okay, so what is the meaning of this? The add symbol, it means the other three atoms are listed anti-clockwise. Now I'm seeing other three atoms. What about the first atom? If there are four atoms, so they are saying you are first looking at the chiral center from the direction of from atom, and then you are talking about the other three atoms, then you are talking about the clockwise and anti-clockwise direction. So what they basically mean to say, the same structure what you are showing here, this I have represented like this, only some new thing you can see here. If you compare this structure with this one, this particular bond has been shown by some this representation. Okay, like here, and this particular F, instead of showing like a single direct bond, they have been shown by this wedge. Okay, they have some directions. So this is the new way of representation, but you don't know this in which side what is there. So how to represent this structure in the correct way? there are actually this particular atom you have to consider like to the central carbon. This you consider to be your central carbon, central atom, on which you have to look from any of these four things. You have to look towards this central atom, and then you have to represent the other connections. So what I'm saying, the center atom here is your carbon atom. So that has been mentioned that that is your chiral center. Now you have to look it from a from atom. So this from atom in this particular case, this you have started from nitrogen. So you are looking towards this carbon from the from atom. So this is you have started your structure from a nitrogen, then you are written the carbon in square bracket, and in that bracket you have to mention whether you are going to read the other three connection like this connection and this particular connection in the clockwise direction or anti-clockwise direction. Okay, so when you are reading this in the clockwise direction, sorry, in the anti-clockwise direction, so then you should represent at. So for this at, you can remember when you are saying it is starting from A, so it is not representing clockwise, but it is representing anti-clockwise. When single at is there, it is representing anti-clockwise. Double at means the opposite of this, so clockwise direction. Now if you see here, remaining three are which atoms? The methyl group, so only hydrogen are removed, so only carbon atom we are considering. Then this fluoro group F, and the carboxylic acid group, again if you remove the hydrogen atom, so carboxylic acid group. So by this representation, what they are saying, you are looking from nitrogen to carbon in the anti-clockwise direction. So carbon they have considered first, then fluorine, and then carboxylic acid group. Okay, when you are changing the direction, then it should become opposite. Like you can start from any atom. There is no thing. You can start from again carbon, but if you are here, they have first taken fluorine. So then and then clockwise direction, carbon will come, and then if you want to start from carbon, then carboxylic acid with group should come next, and then fluorine should come. So this is, I'm sure many of you are not able to uh, predict how this is done. This I will explain in more detail tomorrow. What how it is exactly this direction is coming as clockwise and anti-clockwise. Those who can just want to guess, they can spend time with this, so you will understand. But in tomorrow I will go into more detail of this. What is exactly the calculate for. So if you have any doubt till this part, you can ask me, or anything related to the earlier software things, you can ask me, or if there are no questions, you can leave the class.